So this is an introduction to regression, and I think regression is the most important topic of Econ 3406, so we're going to spend some time discussing it in these slides. Just to recap, we're going to use some concepts that you should know before: mean, standard deviation. And we're going to use another concept that you should have learned about in Econ 3402, and that's the correlation coefficient. And what regression does is traces out a straight line relationship between two variables. And the correlation coefficient is something that we used in Econ 3402 to unpack something about the sign and form and strength of relationships. So in particular, the correlation coefficient is something that we use to tell whether or not when one variable is going up, the other variable is going up as well, or vice versa. When it's going up, it's going down. We also use the correlation coefficient to tell whether all of the points are fairly close to a trend line or whether they're far away. So let's take a look at what this correlation coefficient is. We're not going to compute it in this class, but it is worth knowing what it is. Correlation coefficient is denoted by R. And what it does is for both x and y, so we have two variables here, we essentially compute a z-score. We compute one for x, we see if x is far away from its mean, and we compute one for y. We see if y is far away from its mean. And we see if it's larger or smaller. So if in this formula you take a look at it, Sx is the standard deviation for x, Sy is the standard deviation for y, Xi is the value of x, Yi is the value of y. And if x is larger than its mean, x bar, the first term is positive. And simultaneously, if y is larger than its mean, y bar, the second term is positive, so when we multiply these two together, it's positive. Now, xi and yi are particular points that we have. And so basically what we're doing is saying, let's fix where the mean of x and the mean of y are. Are the points, when x is large, is y also large? We can evaluate that. When x is small, is y also small? And so if x is small when y is small and x is large when y is large, we think there's a positive relationship. So the points are going from the bottom left to the top right. We have a positive slope if we draw a line through the data. If x is large when y is small and vice versa, then the data are negatively related. So basically, if one of the terms is positive and the other is negative, we think we're going to get a negative slope of our trend line. And if they're both positive or if they're both negative, we think we're going to have a positive sign. Now, let's say we have a lot of dispersion. So sometimes we have positive, positive, sometimes we have negative, negative, sometimes we have positive, negative, sometimes we have negative, positive. If the points are spread all over the place, we think that's a weak relationship. If most of the time we have indications of a positive relationship, R is going to be greater than 0. And if R is close to 1, we have a strong relationship. Now, if R is less than 0, that means that when x is large, y is small. When y is large, x is small. And if R is close to -1, that means we have a strong negative relationship. And so the correlation coefficient, that's something that you should have learned in Econ 3402. We spent time calculating it. We're not going to do it again here. But the correlation coefficient is really important in that it determines wholly the slope of the trend line. So it is going to tell us whether the line is going up and the line is going down. So the purpose of regression is to fit a trend line through the data. Trend line is just another term for any type of line. And what we're going to do is we're going to use information that we already have on x and y to form the line. So we're going to use all of the points. We're going to calculate the mean of x and the mean of y. Those 2 points are always going to be on the line. So whenever you make a line through the data, the mean of x and the mean of y should be a coordinate pair on the line. Any line is going to have 2 features. One's going to be the slope, the other is going to be the intercept. The slope tells us how much y goes up when x goes up by 1 unit. So if If I have a slope of minus 0.33, that means when x goes up by 1, y goes down by minus 0.33. If I have a slope of 2.4, that means when x goes up 1, y goes up 2.4. The intercept gives us a prediction for when x is 0. So we have to start our line somewhere, and that's what the intercept tells us. We are going to estimate the slope of the relationship. It's our estimate for the relationship between x and y. We call it beta hat. Beta hat. So there may be some true relationship between x and y. I only see some of the points associated with x and y, and I use those points to estimate the relationship beta hat, understanding that there is some true relationship beta. I don't know what the relationship is, that's why I use the hat. Our estimate for the intercept is called alpha hat. So in an algebra class, you have y equal mx plus b. In this class, we're going to have y hat is equal to alpha hat plus beta hat x. Beta hat is our m, it's our slope. Alpha hat is our b, it's our intercept. How do we fit a trend line through data? We use a 5-step process. First is to find the mean of x. The second is to find the mean of y. I'm sorry, there should be actually just one step. Finding the mean of x and mean of y is the first step. Finding the standard deviations of x and y are the second step. Finding the correlation coefficient is the third step. So these metrics for determining dispersion of data that we learned in ECON 3402, they show back up here. Mean of x, mean of y, standard deviation of x, standard deviation of y, correlation coefficient. The slope, beta hat, that's our estimated relationship between x and y. So think of it like this. Take any relationship you want. Let's look at the one between how long you spend at the mall, x, and how much money you spend, y. Probably positive. The more you spend at the more time you spend at the mall, the more money you're likely to spend. Not 100%. Some of the time you go in, you know what you want to buy, and you leave. Other times you're shopping. I observed some of the data associated with how long I spent at the mall and how much money we spent shopping. I don't observe all of it. So beta hat is an estimate. How do we come up with this estimate? Well, we look at the average amount of time that people spend shopping and the average amount of money that they spend. We look at the dispersion. Some people spend more time shopping, some people spend less, some people spend more money, some people spend less. So there's a standard deviation of x and y, and then we look at the correlation coefficient. So it may be the case that some people spend very little time at the mall and spend a lot of money, but we're also going to observe some points where some people spend a lot of time and a lot of money, some people spend little time and little money, and it's probably not that many people who spend a lot of time and very little money. So we're going to see something that determines whether the slope is positive or negative. The reason the correlation coefficient is important, it determines whether it's positive or negative. So the correlation coefficient determines whether the line is going up or down. The standard deviation of y and standard deviation of x help us determine the magnitude of the slope. That's our fourth step. So if we're recapping steps, the first step is to find the means of x and y. Second, standard deviations of x and y. Third, correlation coefficient. Fourth, the slope. I take the correlation coefficient times the ratio of standard deviations. Y goes first, y goes first, it's on the top, change in y over change in x. Standard deviation of y is physically measuring our change in y. Standard deviation of x is physically measuring our change in x. And I think a good way of looking at it is that these are always going to be positive, so the only thing that can help us determine whether the line goes up or down is the correlation coefficient. Step 5, our intercept, we take the mean of y, which we know is a point on the line, or a coordinate on the line, and we subtract the slope times the mean of x. So the only point that we know for sure is on the line, the mean of x and the mean of y, and that's why we use it to find the intercept. Okay, so let's take a look at an example. Now, on a test, I'm going to probably have you calculate the means, but the standard deviations and correlation coefficient will be provided. The slope. I take the correlation coefficient times the ratio of standard deviations. So let's pretend the mean of x is 1, the mean of y is 3, so I know 1, 3 is going to be on the line. Standard deviation of x is 2, standard deviation of y is 4, the correlation coefficient is 0.6. I take 0.6, I multiply it times 4 over 2, I get 1.2. The intercept, I take the mean of y, which is 3. I subtract the slope, which is 1.2, times the mean of x, which is 1, and I get 1.8 as my intercept. What is my line? It's 1.8 plus 1.2x. Okay, so if I'm starting to draw the line, I start at 1.8 and I go up 1.2 over 1, but I think it's more reasonable just to draw it through the mean of x and the mean of y. This is an important component of this exam, so I will have you fit a trend line through data. And it is very doable. We have to follow this process. There is information that we want to glean from the regression procedure. The first is what's called the residual. The residual is the difference between the actual data point and the predicted data point. We have a term for the residuals called epsilon. Epsilon is this thing that looks like an E. The residual, I think in ECON 3402 may occasionally have been called prediction error, and that's just saying that our line makes a prediction and it doesn't hit the physical data point associated with that particular value of x. So the line predicts a y, but the actual y is a little different. We take the actual data y, we subtract the prediction y hat to get a residual. Now, there are some really desirable things about any trend line that we form. First is that the sum of residual is 0, and this is super cool actually. So no matter what line we form, we're not going to systematically miss up or down, and that's really good. So by following this 5-step process, I guarantee that no matter what my data look like, I'm not going to draw a line that's too high and I'm not going to draw a line that's too low. I'm going to draw a line that doesn't systematically miss up or down. Now, is it going to miss? Of course it's going to miss. They're almost certainly going to miss, but we're not going to keep missing in the same direction. So there's no obvious way to improve the line that we draw. This is called least squares. So the residual is the difference between the actual data point and predicted data point. It sums to 0. And every line that we fit minimizes the sum of squared residuals. So let's say I were to take every data point that I have and calculate how far it is away from the line. And I square that number for each data point. So I'm going to get some big number. Now I'm going to have you try this on your problem set. You're going to try to square the residuals, and we'll work on an example of how to do this. Least squares says that I'm going to pick the line with the smallest squared residuals. So I could have a bunch of lines that miss by 0 on average, but I'm going to pick the one where the points missed by the least amount of distance. And the nice thing about it is that the procedure we choose automatically does this for us. So it's not as if we have to do this physically, pick a bunch of different lines, try to see if it has the lowest least squares. The line that we form from this procedure automatically has the lowest least squares. So let's recap. We have a process to fit a line through some data. We are always able to fit a regression line through our data points regardless of whether there's a relationship between x and y. So we're always going to be able to calculate a correlation coefficient no matter how stupid it is. We can always find the mean of x. We can always find the mean of y. We can always find the standard deviation of x. We can always find the standard deviation of y. So I'm always going to be able to fit a line through some data. I'm never going to have a problem there. That doesn't mean that I should be doing it. And let's go over an example. So let's say I'm watching The Walking Dead, and I am also looking at how many problem sets are completed. Now the problem sets are my x, and the number of zombies I see in The Walking Dead are y. I can certainly estimate this relationship. So here is the line that I estimate. I have zombies y is equal to 24 plus 0.5 problem sets. So if I interpret the line literally, which I could form very easily, I just take a look at the average number of problem sets I receive, the average number of zombies I see, standard deviations, correlation coefficient, boom, I have a line. What it means is that if I get one more problem set, I see half a zombie in The Walking Dead. Now I can use the line to make a prediction. If I receive 24 problem sets, I plug that in. 24 times 0.5, that's 12, plus 24 is 36. I'll see 36 zombies. Now all of you are thinking, if you're listening to this, well, this is clearly a dumb idea. I should not be using the number of problem sets that I receive to estimate the number of zombies that I see in The Walking Dead. This is nonsense. We know there's no relationship between the two. However, if I estimate the relationship between the number of people in a state and the GDP of a state, there's going to be a relationship there. So where does this leave us? I have these circumstances where I estimate lines that have no relationship between each other and ones that do. And I have to be able to distinguish between the two, because I'm always able to form a line through the data. So it doesn't matter what data you have, you can fit a line through it very easily. It doesn't matter what data you have, you can estimate a regression model. We need to be able to distinguish between two possibilities. One, the line we estimate is not indicative of a true relationship between X and Y. Two, it is. So either it is or it isn't. We'd like to know when we are reasonably allowed to think that there's a relationship there. Because clearly with the zombies problem set example, there's no relationship there. And we shouldn't be thinking that there is one. It's problematic if we do. I want to get back to these ideas behind regression very quickly. I want to first talk about the assumptions we need to fit a line in general. The first is that we have a linear relationship in the population. And whenever I teach this, I always like to look at the example between age and how fast it takes to run a mile. So if you look at 2-year-olds, they have really small little legs, and it takes them a very long time to run a mile. Now, if you start looking at high school students, it takes them a shorter amount of time. College students are about the same as high school students, but then if you look at people who are 70, 80 years old, they can't run a mile very quickly. So you have, originally the line is high, then it falls, then it's flat, then it's high again. This is nonlinear. If you try to fit a regression line through this problem, it's not going to work. Anytime I have data that are nonlinear, I shouldn't be fitting a least squares regression line through it. The second is that the standard deviation is the same for all values of X. And what this means is that how far the data are spread apart for when I have small values for X is the same as when I have large values of X. The third is that we have a random sample of data. Obviously, if I'm picking and choosing what data points I have, I ought to be able to make a really nice line. So hopefully, if you want to prove that, eating more Snickers helps you run a mile faster, what you should do is you should throw away all the data where people are eating a bunch of Snickers and they're slow, keep the ones where people eat Snickers and they're fast, and boom, you have a nice line. Is that useful? No, but you could do that. Residuals are normal, that's the last one. So let's go back to the idea behind regression. Different values of X are going to generate different values of Y. So take a look at the number of years you're in school. We think that one of the main reasons you attend college is not because you love learning so much, but because you think if you're educated for more years, you're going to have a higher income. That's sort of a goal that most people have. Obviously, people with low levels of income or low levels of education, have lower average incomes. That doesn't mean that there's not a distribution. So we all know people that graduated from high school and earn lots of money. And we also know people that graduated from high school and are not working in any appreciably important position. We also know people who are college graduates who work the same job that they have in high school, but you're in college because you think that that's going to be different for you, and that you're going to earn more money than you would have otherwise. And so we understand that lower education, lower average income, higher education, higher average income, but we also know plenty of counterexamples. And the idea behind regression is we're going to draw a line that connects the means, and if there's more and more dispersion around these values, we start to think maybe it's not that valuable to fit this line. Okay, so let's go back to this idea very, very quickly of dispersion around different mean values. How are we going to measure how dispersed different incomes are for a level of education? We physically take the data, compare it to the line. And larger residuals are indicating that the data are more dispersed. So if all the data are really far away from the line, I think the standard deviation of the regression is really high. And the reason for why I think that is because here's the line, none of the points are anywhere near the line. So this is useful because we get back to this idea of trying to distinguish between two possibilities. One, that there's a relationship between x and y. The other is that there's not. We start to think that there's no relation between x and y when the data are spread everywhere. And the reason we think that is when we plug a value into the line, if it doesn't come anywhere near the data, then what good is the line? Does it really help us predict? How do we measure that? We're going to calculate what's called the standard deviation of the regression. What is this? We take all the residuals and we square them. We add them all together. We multiply by 1 over n minus 2. N is the number of observations that we have in the regression. If you see here, we have the data on y, we subtract the intercept, we subtract the slope times x. Practically speaking, this is our y is the data, alpha minus the slope times x is the prediction. Those are residuals. So we square all the residuals, add them together, multiply by n minus 2. We use up one observation to find the mean. The second finds the standard deviation. That's why we lose 2 observations. Practically speaking, you can never fit a regression through just 2 data points because it's like playing connect the dots. And you're never going to have any variation there. You're always going to have the line fits those 2 data points perfectly. And so you need that third data point to give you an idea of whether the line actually fits, because if I just have 2 data points, it'll fit by default. Okay, so standard deviation of the regression is something I'm going to have you calculate. Well, I have you calculate these residuals. This is what's called the sum of squared residuals. The answer is no. I give everyone the sum of squared residuals. And what we want to know is if the slope is actually different from 0. So if there is some true relationship between x and y, that's nice, but all we have is an estimate of the relationship. If we have different points, we have a different estimate of the relationship. And just think about this class. Let's suppose I wanted to estimate the relationship between your parents' income and your income. If I take the first 15 people, I'm going to have one line. If I take the next 15 people, I'm going to have a different line. If I were to shuffle the observations, I might have a third line. If I take more observations, I might have a fourth line. And which of these lines represents the truth? That's not something we're going to be able to figure out, but what we can figure out is it reasonable to think there's a relationship between parents' income and your income for any of the lines? So what we're going to do is we're going to follow a strategy for testing a hypothesis related to the slope of the line. First, we're going to state the hypothesis. What we do in this case is we say the null is that there is no relationship whatsoever. So we start from a position where we're at point 1. The line we estimate doesn't indicate a relationship. That's the null. And 2 is the alternative, where there is some relationship. We're going to construct a test statistic. We're going to use 4 pieces of information. First is the claim. That's 0. Second is the sample slope. That's what we use the process to find. Third is the standard deviation. That's what we use the residuals for. The fourth is what's called sum of squared deviations, where we take x, we subtract the mean, and we square it. Kind of gives us a feeling like the number of observations in the sample size. Both 3 and 4 will have major components provided. The test statistic looks like this, and we're going to work on calculating it.